Planck's black body spectrum is a consequence of the quantum nature of reality. If one is to use exclusively classical physics, then one would predict that a black body emitting light will give off an infinite amount of light at the very shortest wavelengths. We can see that the classical prediction for the amount of light emitted from a perfect black body will blow up and go to infinity as the wavelength goes to zero. However, this is not what is observed. We observed that the intensity of the light does reach a peak, but then falls back down to zero as the wavelengths become very short. By proposing the existence of discrete packets of energy, in other words, by proposing the existence of photons, Max Planck was able to predict the observed spectrum of radiation inside an oven, or emitted from a hot black body. When we investigated electromagnetic waves in a previous section, we suggested the existence of light by applying Ampere's law and Faraday's law to a wave solution. Let's think about what we did. We asked the question, is it possible to have a solution to the electric and magnetic field if there are no sources of the electric and magnetic field present in a region? In other words, if we have a region where charge Q is equal to zero and current I is equal to zero, are there any solutions to E and B other than E equals zero and B equals zero? And it turns out there is a non-trivial solution. By applying Faraday's law and Ampere's law, we find a wave equation. So we predict the existence of electromagnetic waves absent any sources for those fields. And in other words, we are able to predict the existence of light without having to assume light exists a priori. You could imagine that if cave fish did physics, then they would be able to learn of the existence of light as soon as they understood about electric charges and electric currents and electric fields and magnetic fields without ever having to actually physically be able to observe light. Now, when we talk about waves, waves have specific properties. They are not localized. They tend to be spread out over a region of space. Waves can also interfere with other waves. They can wrap around objects and so on. And we observe light to possess many of these properties, so we might be well motivated to conclude that light can be described as a wave. When I say waves interfere, that is basically a phenomenon where when two or more waves occupy the same region of space, you add their amplitudes together to get a resulting height of a wave at every location. So if you imagine two waves that have the same wavelength and are perfectly lined up with each other, then the peaks will line up and create an even higher peak. The troughs will line up and create an even deeper trough. And this is known as constructive interference. On the other hand, if you shift one of these waves over by half wavelength, then the peak of one wave will line up with the trough of the other wave, and the trough of the first wave may line up with the peak of the second wave, and these waves will completely cancel each other out. Now, there is a more rich phenomenology for ways that waves can interfere. You could have waves of different wavelengths or different amplitudes, or 3 or 4, or any number of waves all stacked on top of each other, and you could get some other interesting pattern of waves interfering with each other. Poisson spots and the Young's double slit experiment are two famous experiments that may lead us to conclude that light can indeed be well described as a wave. In the Young's double slit experiment, monochromatic light was shined at a screen, and that screen contained two very small slits in it. The majority of the light that hit this first screen was just absorbed by the screen, but a little bit of the light was able to pass through these two very small slits. We want this light to be monochromatic because we want all the light waves to have the same wavelength. So you could imagine that the solid lines are the peaks of the light waves approaching the screen, and the dashed lines are the troughs of the light wave approaching the screen. Now, for the light that is able to pass through the slits, whenever one peak passes through one slit, a peak will also pass through the other slit because we are assuming we have a nice uniform wavefront. You could achieve this by having the source of your light be very far away from the screen. Now, when the light passes through these two slits, in some locations, the peak of the light waves that pass through one slit will overlap with the peak of the light that passes through the other slit. And when the two peaks overlap, we will have constructive interference, and the light will appear even brighter at the location where those two peaks overlap. In some other locations, you might have a peak from one slit overlap with a trough from the light emitted by the other slit. And in those locations, we will have destructive interference and you will see no light at all. If light is to be well described as a wave, we would then expect an interference pattern to appear on the screen back here, varying locations where there are bright spots and dim spots, including right between the two slits in the first screen. And indeed, that's what we observe. So this experiment seems to conclusively demonstrate that light can be well described as a wave. If light were well described as a particle, then you would expect most of the particles of light will be absorbed by the first screen, but a few particles of light will travel through the slits, and those particles will just travel and hit the screen in the back, and you would have two locations on the back screen where the light hits and nothing else. The fact that we see this interference pattern strongly suggests that light can be described as a wave. The Poisson spot is another famous experiment that strongly suggests that light should be treated as a wave. In a Poisson spot experiment, a source of monochromatic light is shined at an object. Some of that light will hit the object and be reflected in a random direction, while other light will miss the object and travel onto a screen behind the object. In a Poisson spot experiment, we observe the shadow cast by this object. Now let's think about what the prediction would be if light is to be treated as a wave compared to if light is to be treated as a particle. If light is well described as a particle, then you would expect that some particles of light will strike the object and be reflected, and those particles of light will not be able to strike the screen directly behind the object. However, other particles of light will miss the object and travel on to illuminate the screen. In this picture, there should be no light appearing in the middle of the object's shadow. On the other hand, if light is well described as a wave, one property of a wave is a wave can bend around an object. So if we have waves of light striking the object and bending around it from various sides, then these light waves might interfere with each other, and we could potentially have bright spots appearing in the shadow of the object. And indeed, this is what we see. If you send monochromatic light at an object, we want the light to be monochromatic because we want the light to be all of the same wavelength to make our experiment simpler. You can see little bright spots of light in the shadow of this object. So this strongly suggests that light should be described as a wave. The Poisson spot and Young's double slit experiment are two very famous experiments that suggest light should be described as a wave. So now comes along the photoelectric effect. The photoelectric effect is a famous experiment that suggests that light should be described as a particle. Let's think about what it means to be a wave versus a particle. We said one property of a wave is non-localized. A wave is spread out over some region of space. On the other hand, a particle is a localized object. A particle is often thought of as a single unit of matter that exists at a single point. And this single unit of matter might contain mass or charge or momentum or some other physical properties that you're interested in. For the picture of light as a particle, light is a particle that has zero mass but will still carry energy and momentum. Albert Einstein proved that light could be described as a particle through his description of the photoelectric effect, and this earned Einstein his only Nobel Prize. Albert Einstein was never awarded a Nobel Prize for his discovery of special relativity or general relativity, which is a more fundamental description of gravity compared to Isaac Newton's theory of gravity, or for his description of Brownian motion, which is widely considered to be the final nail in the coffin that conclusively proved atoms exist. So what is the photoelectric effect? It is observed that when light is shined on a metal, electrons might be emitted from that metal. Light will not always cause electrons to be emitted from a metal. For this effect to occur, that light must possess a minimum amount of energy. The minimum energy necessary to liberate electrons from a metal is known as the work function of the metal. The work function can also be thought of as the energy by which the most loosely bound electrons are bound to the metal. If we transfer an amount of energy greater than the work function to those electrons, then those electrons will be able to stream away from the metal. So what is happening in the photoelectric effect is that light will strike the metal and be absorbed by the electrons. If the energy of that light is greater than the work function of the metal, then some of that energy will go into liberating the electrons from the metal, and whatever leftover energy there is will go into the kinetic energy of the electrons as they stream away from the metal. Because the energy of light can be written as h times the frequency of light, or hc divided by lambda, we could also write hc divided by lambda equals W plus Ke. What we observe is that light with a low frequency, in other words, light with a large wavelength or low energy color of light, will never cause electrons to be emitted from a metal when that light is shined on the metal. However, if the light has a sufficiently large frequency, in other words, if the light is of sufficiently short wavelength or sufficiently high energy, then electrons will be liberated from a metal when that color of light is shined on the metal. As an example, let us consider the metal potassium. Potassium has a work function of about 2.3 electron volts. A photon with energy of 2.3 electron volts will have a wavelength of around 540 nanometers. When we work on photoelectric effect problems, energy will very often be given in units of electron volts instead of units of joules. An electron volt is just a unit of energy, and you could always convert between electron volts and joules when you work on these problems. I want to caution you that when you work on these problems, be aware of what units H is given in. Planck's constant is sometimes written in units of joules times seconds, but it is also very common to find Planck's constant written in units of electron volts times seconds. Both of these are used very often, so be aware of what units you're working with when you consider these problems. So we would see that if we shine light with a wavelength of 680 nanometers on a potassium target, there will be no electrons ejected from that potassium target. If instead we shine light with a shorter wavelength, implying light with a higher energy of 550 nanometers on a potassium target, then that light would be sufficiently energetic to cause electrons to be ejected from the target. We would see electrons streaming away from the target, and the maximum velocity of those electrons would be 3 times 10 to the 5 meters per second. Some electrons will be moving slower than this maximum value. The reason for that is some of those electrons are more tightly bound than the work function of potassium, and therefore it will take more than 2.3 electron volts to liberate those electrons, and therefore there is less leftover energy to be converted into the kinetic energy of those electrons. Also, if we shine even greater energy light on the potassium target, then there will be an even greater maximum velocity of the electrons that are liberated from this target. At this point, you might want to say, but wait a minute. You are saying that if we shine light with a wavelength of 550 nanometers on the potassium target, electrons are liberated. But up here we say the work function of potassium is 2.3 electron volts, and that corresponds to a photon with a wavelength of about 540 nanometers. So we should have photons of wavelength 540 nanometers or less be energetic enough to liberate electrons from a potassium target. Doesn't this wavelength of photon imply that the energy is not large enough to liberate electrons? And if you were to ask that, I would say you are absolutely correct. This picture was taken from an observatory's official website, and there is a typo in it. It is okay to occasionally make mistakes. Everyone does it. If we shine light on potassium, which does have a work function of 2.3 electron volts, and we observe the maximum velocity of those electrons is 3 times 10 to the 5 meters per second, then the wavelength of light that we shined on this sample of potassium was actually 485 nanometers. How does the photoelectric effect demonstrate that light can be described as a particle as opposed to a wave? To address this question, we will again consider the possibility that light can be described as a wave and ask ourselves what we expect to observe in the context of this experiment. We will ask ourselves, if light is a particle, what do we expect to observe in this experiment? And then we will compare these expectations to what we actually observe. If light is not a particle, in other words, if light is a wave, then I would expect that a low energy, or in other words, a long wavelength source of light should eventually be able to liberate electrons from a metal. As more light is shined on the metal, more light, or in other words, more energy, will be absorbed by the electrons in the metal, and eventually those electrons will have accumulated enough energy that they can be liberated from the metal. Because a wave is an object that is spread out over a region of space, we expect the energy contained in the wave to also be spread out over a region of space. Contrast this description with the picture where light is described as a point particle. If light is a point particle, then all the energy contained in the light should be entirely localized to one specific point in space. In this description, the electrons in the metal will absorb all the energy from the light at once. There will be no gradual buildup of energy until the electrons have enough energy to be liberated from the metal. If light is described as a wave, then we expect that all we have to do to liberate electrons from a metal is to shine light on the metal until the electrons have enough energy to be emitted from the metal. If the light has a very long wavelength, in other words, if the light has a very low energy, all we have to do is wait a bit longer, but eventually we would expect the electrons in the metal to accumulate enough energy to be liberated from the metal. But this is not what we observe. What we observe is that the electrons are only liberated when the color of the light shined on the metal is sufficiently blue. In other words, the light has a sufficiently short wavelength or sufficiently high energy. If the light does not have enough energy, if the light has too long of a wavelength, then electrons will never be liberated from the surface of the metal, no matter how long you shine the light on the metal for, and no matter how bright you make that light. This suggests that energy is either absorbed by the electrons in the metal or it is not, suggesting that all the energy in the light is contained in one specific point in space, implying the localization of the energy, or in other words, the existence of a photon. According to the photoelectric effect, light can be correctly described as a point particle. The photoelectric effect tells us that light can be correctly described as a particle. Young's double-slit experiment and the Poisson spot tell us that light can be correctly described as a wave. Since the beginning of Physics 121, we have treated matter such as baseballs and electrons as particles. One might therefore be inclined to ask, can we reasonably treat matter such as baseballs and electrons as waves? And it turns out the answer to this question is yes. Matter with a momentum p can be described as a wave with a corresponding wavelength given by lambda equals h over p, where h is Planck's constant and p is the momentum of the particle of matter that we are considering. This is known as the de Broglie wavelength. Looking at this equation, we can see that for everyday macroscopic objects such as baseballs and limes, the typical wavelength will often be very small as a result of h being on the order of 10 to the minus 34. On the other hand, an electron has a mass on the order of 10 to the minus 30 kilograms. Because the typical momentum of an electron is much smaller than the typical momentum of a macroscopic object such as a baseball, the characteristic wavelength of an electron will be much larger than the typical wavelength of a baseball, and this makes the wave-like behavior of an electron much more easy to detect in an experiment. Because objects that we typically think of as particles do display wave-like behavior, such as wavelength and frequency, this implies that any experiment that is set up to detect the wave-like behavior of light can be modified to detect the wave-like behavior of particles as well. Young's double slit experiment was modified to test for the wave nature of particles of matter. A beam of electrons was directed towards a screen containing two small slits, and any electrons that passed through that screen would be projected onto a screen further back. When checked, that screen further back did display an interference pattern, suggesting that a beam of electrons could be treated as a wave. This experiment was then further modified so that only one electron would be traveling through our double slit apparatus at any given moment. In practice, this could be accomplished by having a radioactive source that decays very slowly. If the radioactive source only emits one electron every second or every 10 seconds, the time between one electron and the next being emitted will be so long that we could practically guarantee that at any given moment only one electron will exist in our double slit apparatus. Nevertheless, even when only one electron is present in our double slit experiment, this diffraction pattern still occurs. This indicates that a particle of matter, such as an electron, can be correctly described as a wave.